I think we may start. We are very happy to have Professor Radu Balan from University of Maryland again. This is another joint month CS lecture, recorded, transmitted. And Radu will tell us about new developments of phase retrieval problem, how we can recover phase that is missing from measurements, or I mean the perspective will be more theory-oriented, probably, from what I heard from Radu. And many people are interested in Radu's results, so we are very happy to have you.
Christoph, thank you much for the invitation and introduction. Thank you all for coming. Happy year. I guess I heard that's starting off a new term, I guess, and the seminar series. It's 13th, but it's not Friday, it's Monday, though, so hopefully it's going to go better. Indeed, today I'd like to talk about new developments on this so-called phase retrieval problem, or reconstruction from the magnitudes of frame coefficients. A problem I started working on a couple of years ago. Well, while I was working in industry at Siemens at that time. Let me actually start by saying my collaborators and sponsors. So I thank the sponsors, NSF and Siemens, my former colleagues from Princeton, whom I still have a collaboration with, as well as my students at Maryland, Mark Lai, Makshan Broich, and Dong-Yan Zhu. Here's an overview. So firstly, I'd like to talk about the problem to, well, state the problem I tried to solve and discuss today in its abstract form. And then I'd like to discuss three specific results, or set of results. One is about injectivity. The second one is about robustness, and those are deterministic and stochastic bounds, Lipschitz and stochastic bounds, the Cramer-Rao lower bound, as you'll see. And the third issue is about algorithms, how to do reconstruction. And I'm going to finish with some simulation results. Okay, here is in a nutshell, if you want the actual problem in the abstract form. So we have a Hilbert space H, finite dimensional. Think of it as Rn or Cn, so real or complex space. And a bunch of vectors, m vectors, f1 to fn. They form a frame. Basically what frame means in this setting is just a complete or a spanning set of vectors. So you have at least n vectors, so m is at least n, but in fact, in order to do reconstruction, think of m as 2n or 4n, or larger than that. Now, in the Hilbert space H, so Rn or Cn, we identify two vectors, x and y, if they differ by a constant phase vector. So this is the equivalence relation on the second bullet. We have any two vectors, x and y. We say x equivalent to y if there exists a scalar z of magnitude 1, so absolute value of z is 1. In the real case, z can be plus or minus 1. In the complex case, z is of the form e to I phase. So that y, the vector y, is this constant z times x. Right? So that's the equivalent relation. Two vectors are equivalent if they differ by a constant phase vector. And think of H hat as a quotient space. So it takes the classes of equivalence, like rays if you have the quantum mechanics. Okay. Now, once we have the set of vectors f1 to fm, we're looking at this nonlinear map alpha, which does the following: takes a vector x and gives you the magnitude of inner products, x with fk. Okay, so alpha is an m-dimensional, alpha of x is an m-dimensional vector, and the case component is the magnitude of x with fk. Alpha, on the other hand, is well defined not only on H, but also on the H hat, on the set of classes of equivalence. Why? Because, well, if you multiply x here by a phase vector z, when it takes the magnitude, you know, this stays the same. Right? So alpha is actually constant on the equivalence class. That's why it's well defined on the H hat. Okay, our main objective is to analyze this nonlinear function alpha, specifically to understand what is injective, and if so, try to invert it. Okay? This is essentially the phase retrieval problem. From the knowledge of the magnitudes of these inner products, we like to recover x. We cannot do so x, the vector x, but the best we can hope is to recover the class of x. That is to say, recover x up to a global phase vector. So this is
more specifically. So alpha, again, is our nonlinear map. And the problems we like to analyze is, first of all, the invertibility, to understand when such inversion can take place, and specifically try to understand the injectivity of this map, alpha. I mean, it's not subjective because, for instance, components of alpha cannot be negative, so you cannot, read the whole RM, but there's not an issue. At least if it's injective, you can still have a chance to find the left inverse. Then the second issue is the algorithms. Okay, if it's injective, how to do so efficiently. And the third thing is robustness of this inversion. So I'd like to understand if, in principle, if alpha can be inverted, how well can we perform such an inversion? So whenever we have an algorithm, you can compare to such bounds. And there are deterministic bounds like Lipschitz constants and stochastic bounds like Cramer-Rao lower bound. We're going to discuss both of them. And just as a bit of notation or definition, we say a frame is phase retrievable or gives phase retrieval when this nonlinear map alpha is injective. Right, so our goal is to analyze, to characterize the phase retrievable frames, and then to find algorithms and characterize the robustness of inversion for such frames. All right. Why is this problem interesting? I mean, the relevance. So historically, actually, it came in X-ray crystallography. And here is a picture I downloaded from Wikipedia. In X-ray crystallography, what people do is the following. You have a crystal which has an electron density that it's repeated in space. It's repeated periodically in space. And you measure a diffraction pattern. From the diffraction pattern, you try to understand the electron density, this function capital R. So the diffraction patterns, the capital I of k, the intensity of these measurements, depends on the wave factor k, and there's nothing else but the magnitude square of the Fourier transform of this electron density. And what the problem is, from the capital I, the diffraction pattern, I like to recover capital R, which is the electron density. So in some sense, that's a very specific form of this phase of the nonlinear reconstruction that we're trying here. However, besides the X-ray crystallography, the same problem actually comes up in some other scenarios. In fact, from my perspective, I was more in the audio and signal processing, and in fact, for me, it was interesting to, I came to this problem coming from the audio signal processing if you want, approach or problem. But similar problems or a similar question is raised also in radar imaging systems and more recently in beam pattern design. I mentioned my collaboration with Siemens, and that is actually along the lines of very large-scale sensor array, beam pattern design for such arrays. Right. So let me start with the first problem, the invertibility. We're going to analyze the two cases separately, the real case and the complex case. Well, the real case is easier and it's much better understood. The complex case, it still has, we made some significant progress in the past 3 years, but there are still some important questions. So in the real case, just to rephrase the notations, alpha in this case maps Rn hat into Rm and takes a vector x and dimensional vector and gives you the sequence of coefficients, magnet of coefficients xfk, which you can also think of it as the by taking the vector x, multiply on the left with this matrix f star. F star is an n by, so f is the n by m matrix, whose columns are the frame vectors f1 to fm. You stack column-wise the frame vectors, and then f star is transpose conjugate. Well, in this case, it's just transpose because everything is real. And then the bars, the outside bars means you take the magnitude entry-wise. Okay, it's not a norm or something, but just take the magnitude entry-wise. So also as a notation, we're going to denote by capital R of x this n by n matrix. Right, so this is sum over frame vectors. So you fix a vector x, a dimensional vector, and it is as if you construct so-called the frame operator. The frame operator is the sum of fk star, fk transpose, the sum over all k's. But actually you weight each such rank 1 by xfk mod square. Right? And you sum over frame vectors. And this is our notation for R of x. Okay. So with this notation is in place, here's the main result in the real case, which says the following, that the following properties are equivalent. The frame f is phase retrievable, so the nonlinear map alpha is injective. And then there are two other conditions which are equivalent to this one. The second one is pure geometric in nature, and essentially says that no matter how you partition your frame set into two subsets, disjoint partition, one of the two must span the whole space. At least one must span the whole space. Okay? So this is a necessary and sufficient condition for phase retrievability. You have the complete set of vectors, and no matter how you partition, one of the two parts, at least one of the two parts should span the whole space. Right? That's condition number 2. Condition number 3 has an analytic component to it, and says the following, that there is a constant A naught, a positive constant, simply positive, so that if you look at this n by n matrix, Rx, I constructed it depending on x, this is not only non-negative, but actually it's strictly positive. It's bounded below by A naught times norm of x squared, because that's how it scales with x, times identity. Okay? That's, in some sense, an analytic condition. This is a geometric condition, and this is what we're interested in, the phase retrievability. Okay? These conditions are equivalent, likely.
Now 3 has to hold for every x.
That 3 has to hold for every x. That's correct. Yes, for every x, they should hold. Okay. Now let me just give you a quick argument in terms of 2 and 3, for instance. Right? Think of, you partition your set F into F1 and F2. Let's say that F1 does not span the whole space, right? If it doesn't span, then you find a vector X, which is orthogonal to all vectors in F1. Right? Let's take that particular vector X and plug it in here in Rx. What happens, it says that, well, when you construct Rx, XFK is going to vanish for a bunch of vectors, those which are indexed in F1, right? Belong to F1. And you are left exactly with a sum of rank 1's XFK square, and then you have exactly this second part. If this inequality holds true, that tells you that the remaining part should be strictly positive, which implicitly means the set of FKs that it's in the second set, in the second leg, should span the whole space. Because if they don't, well, you find another vector y, you hit with both sides y, y, this would be 0, and you get a 0 here, which would contradict this inequality. Right? And basically, the converse is also true. If Fk spans the whole space, well, you cannot have all this in that case, even though XFK would vanish for some, it's not going to vanish for the remaining part. It cannot be orthogonal on the remaining part. You can maybe get a few more vectors Fk which are still orthogonal on X, but the remaining part, they still should span the whole space. And that statement would guarantee that R of X is invertible, which eventually you get such a lower bound. That is to say, if you know that R of X is always invertible for non-zero X, then you can find an A naught bound that satisfies it. Right? And the fact that R of X is invertible, it's equivalent to the fact that if you choose an X which is orthogonal on some set of vectors, definitely the remaining one should span the whole space. This is what it is. All right. So that's maybe in a nutshell why 2 and 3 are equivalent. And eventually they turn out that those conditions are equivalent to 1 as well. As an immediate corollary of this result, it says that you need to have at least 2n minus 1 vectors. So in the real case, you have to have at least 2n minus 1 vectors in your frame in order to be phase retrievable. Why is that? Well, if you have 2n minus 2, well, you can always split into n minus 1 and minus 1, and clearly none of them can span the whole space, which is n-dimensional, right? So that's why you have to have at least 2n minus 1. It's not sufficient any 2n minus 1. Of course, if you take one vector and you hit 2n minus 1 times, it's not going to provide you enough information, so you have to have more than that. But it's not only the number, but also the some sort of the clearly the orientation, the relative orientation is important. Well, condition number 2 is technically you could check in a finite number of operations, right? It could. The number of operations, if you can grow pretty fast to pretty large numbers, because technically it's it's a combinatorial condition. You should check, a possible combination. It's true, but nevertheless, you can do it in a finite number of steps. That's the good news. Well, the bad news is combinatorial. The good news is finite number of steps. Why it's good? Because you'll see in the complex case, you don't have even that kind of condition, unfortunately. So that's why it's nevertheless a good condition. It's a good. All right. So that's the real case. Let's start now with discussing the complex case. So the complex case I mentioned is a little bit more complex. We have the m vectors, F1, Fm, is Cn this time. Capital Fk is going to denote this rank 1 matrix. So it takes the vector Fk, transpose conjugate, and you get an n by n symmetric matrix. This is complex symmetric Hermitian. Now, for each vector, like Fk, n-dimensional complex, we associate a 2n-dimensional real vector. Right? This map J maps a complex vector n-dimensional in 2n real vector by splitting real and imaginary parts in computation. Yeah? Real part the first and component, imaginary the second. And with such a thing, we, for vectors Fk and therefore Vk, we construct this matrix capital Vk, which is 2n by 2n, symmetric real. Right? So it's done in this way. So you take the Vk vector times transpose, but also you add another rank 1 by multiplying Vk on the left with this matrix J, right? And then transpose conjugate with J transpose on the right side. So the capital Vk is rank 1, right? However, the capital Fk is rank 1. The capital Vk here, however, is rank 2. Right? Note this difference. So this is rank 1, but has complex entries. Complex is a Hermitian matrix. And by n, this is a rank 2 real matrix, 2n by 2n, right? So as I said, capital Vk is a 2n by 2n rank 2 symmetric, real symmetric matrix. Okay, why do we do this? Oh, one more thing. So for two complex vectors, or two vectors, u and v, we're gonna introduce this symmetric order product as uv star plus vu star, 1/2 of the sum. Right, so it's a vector times transpose conjugate plus the conjugate of this and the average. For instance, u equal to u, this reduces to u star, rank 1. Right. As an interesting thing, it turns out that, well, maybe it's not that obvious, but nevertheless it's true that not only this is a rank 2, this is obvious, but actually it turns out that it has exactly the two non-zero eigenvalues, if it's rank 2. The two non-zero eigenvalues, one must be positive, the other must be negative. May not be obvious, and in fact I did not know until maybe a year or so ago when I started looking more to this thing. This is exactly what it is. And any rank 2, which one positive, one negative, you can write it like this for some UV vector. That's anyhow. Now, a little bit more things. So any n vector x, we associate psi. This is a 2n real vector, it's real imaginary as before. And we're constructing now this matrix Rx, which is a 2n by 2n symmetric matrix. Or we can write in terms of x or the psi vector just as well. And it's a sum of rank 1s, so m rank 1s. And the rank 1s are obtained in this way. So you take this matrix Vk, right? This is a rank 2, 2n by 2n. You multiply with the vector psi, and then multiply by transpose, right? And sum over k. Okay. For the time being, it may look strange. I mean, I know it's a bit of notation here, but bear with me for a little bit. You'll see that this, in some sense, plays an analog of the Rx we had previously in the real case. That there is a 9 constructed this way. All right. So here's the main result, I'd say, in this case. So I have to say that actually similar results. I mean, some of the statements of this here appeared independently in a recent paper by Afonso Bandeira, Jameson Cahill, Dustin Nixon, and John Nelson, which actually going to show up appear in the ACHA sometime, I guess, this year. The frame F is phase retrievable. Okay, so now what is this equivalent to, right? What are the equivalent conditions? So condition number 4, let me start with this one first. This is actually the equivalent in the real case by saying that there exists a positive constant A0, so that for all vector psi, 2n real vectors, this matrix R of psi, defined this way, is bounded below by, well, it's not just simply A0 norm psi squared times identity, unfortunately. There is actually a different object, which is a projection that shows up. It's a 2n minus 1. It's a rank 2n minus 1 rank projection that shows up as a lower bound, not the identity. Okay. I'm going to comment a little bit on the meaning of this one, and instead of that identity, you get a projection. The other two conditions, number 3 says that if you stack these m columns together, so you apply that rank 2 on this vector psi, what you get an n by m matrix. Okay? It says that the rank of this guy should be 2n minus 1. Now, just to understand the relationship to the real case, basically in the real case, the capital Phi1 is just capital F1, is a matrix of the frame vector F times transpose, it reduces to that one, and times psi and so on. If you construct this similar matrix, what we get is that for every non-zero psi, this matrix should have exactly rank n, should be full rank. That's equivalent to saying that no matter how you split, one part should span the whole space. It's equivalent to saying that these matrices all would have full rank, and that would be n. Here, however, the full rank would be 2n, because these are 2n by 2n matrices and so on. You would expect that this would have full rank, would be 2n, but actually that's not possible. It's provable that they always have a vector in their kernel, that is to say, there is a vector, so you multiply on the left, with transpose you always get 0, and that is j times psi. J times psi vector always, when you multiply on the left, the transpose always vanishes this matrix. So this cannot have 2n, rank 2n. But what the condition says is that this is the only vector in its null space. If you want B transpose in the null space of B transpose, that's the only vector in the null space. And if it's 2n minus, and in that case it would be rank 2n minus 1. And that is actually responsible why the lower bound here is not the identity, but it's a projection of rank 2n minus 1. And that turns out to be equivalent to the phase retrievability. Number 2 condition, I'm not going to mention too much about it here, except to say that eventually it has a bearing in terms of the Lipschitz constants. And the same bound A0 that you use here in condition 2, actually you can use it in condition 4. So it's exactly the same bound. Okay, so that would be maybe in a nutshell a little bit of explanation as to why the conditions look like this. I mean, are a little bit more complicated than in the real case. And the main difficulty is the fact that some of the similar objects to the real case have some null space, which in the real case they did not have. You have to take into account this null space. Right? So that's a geometric nature. Okay. All right. Okay, what about the critical redundancy? In the real case, we said it's 2n minus 1. And because that's equivalent to the geometric decomposition, no matter how you split, you have one part should span the whole space. And with 2n minus 2 or less, you cannot do that. Here, unfortunately, we don't have that simple geometric condition at play. That is necessary, but not sufficient. It turns out that the following statements are known and are provable. You need to have at least 4n minus some order log n vectors. That's a strange number. Actually, it's a very specific bound. It's a number of ones in the binary representation of n minus 1. I mean, it's a very concrete number, but it's kind of weird. And that is provided that n is a, I think, either 0 or 1 modulo 4. In other cases, there are some other additional 1 or 2 that you have to add. So that's why I'm saying it's order log n. This comes actually from a deep result in topology, in algebraic topology, late 60s, when people we're trying to analyze the complex projective space, and when complex projective space can be embedded, what is the minimal real embedding of complex projective space? And analyzing the Chern numbers for the complex projective space, that's how they come up with the 4n minus order, this log 2n minus 1. Anyhow, this is a lower bound. Now, in terms of the upper bound, we know the following, that 4n, at least we knew, let's say a month ago, 4n minus 2 is sufficient generically. Generically with respect to Zariski topology, meaning that if you just take a random frame set with 4n minus 2 vectors, with probability 1, that would be sufficient. Actually, recently, that is in the last months, Dan Edidin and his collaborators showed that in 4n minus, so we knew that 4n minus 4, there exists a case 4n minus 4, an example of 4n minus 4 frame vectors, for example, map alpha is injective. We also knew that the set must be at least open, but in fact, he showed that it's also dense. So 4n minus 4, if you want, is the optimal bound at this time, for the upper. And yeah, so there is a conjecture that says that 4n minus 4 is actually a critical threshold here as well, but we are not yet able to show that. Some people believe that that's a threshold. Anyhow, roughly speaking, redundancy 4. That's what it is, right? Up to some logarithmic factor most. This is a complex case. Okay, now let me discuss a little bit about the robustness measures first, and then towards the end discuss the algorithm. And I do so because some of the objects we introduced earlier have relevance here. So I'll start with the Cramer-Rao lower bound first. And for the Cramer-Rao lower bound, we assume the following measurement process. So we measure the magnitude square of this of the frame coefficients, to which we add noise. This is additive white Gaussian noise. Okay, so we assume this measurement process: magnitude square of frame coefficients plus Gaussian noise. And let's assume that these are IID, independent identity distributed random variables and noise, and these are normals, mean 0 and variance sigma squared. Okay, what we want to do is to derive the Cramer-Rao lower bound for this problem. Okay. And first step is to derive the Fisher information matrix. It turns out that once you do the computations, the Fisher information matrix, which depends on the vector x, it's exactly 4 divided by sigma squared times that matrix R I introduced earlier. That's the reason actually I had a similar notation in the two cases, real and complex. And then it has actually it's exactly related to this Fisher information matrix for our problem. Okay. The Fisher information matrix, if you're not familiar with that, you take the log likelihood for our problem, you take its gradient with respect to the parameters, in this case x, okay, form of vector. In the real case, let's say transpose conjugate multiplied by transpose conjugate, and do expectation with respect to noise. The random part. And this is what comes out for the Fisher information matrix. When you do actually the computations for this problem, this is algebraic to this, you obtain this expression. So again, in the real case, this is 4 by sigma square, and then it's a sum of rank 1s, right? And the rank 1s are obtained by applying fk on x times transpose conjugate. Right. In the complex case, it's also a sum of rank 1s. Rank 1s are that matrix capital K applied on the side, which is a 20 by 20 rank 2 capital K. But when you multiply the sides, of course, it's one vector transpose conjugate itself, you get rank 1. This is the matrix capital R of x in the real or complex case, right? And I brought them to be comparable so you can have it. Now, once we have the Fisher information matrix, we want to do something with it, right? And typically, it provides such a robustness measure, so-called the Cramer-Rao lower bound. Now, I want to present two different cases, which are interesting. So, case number 1, I call the no oracle case. All right, so there is some text here. Here's the framework. So fix a vector z0 in the Hilbert space. It's an n-dimensional error complex. Right? And now I denote by capital omega sub z0. In some sense, it's half space. In the real case, it's exactly the half space, right? Which contains a vector z0 and basically all vectors which are on the same side as z0 with respect to the perpendicular hyperplane, right? Because inner product is a set of vectors in H, so the inner product x with z0 is strictly positive, right? So in the real case, you have the vector z0, think of the hyperplane perpendicular to z0, and the omega z0 is 1/2 of the space. Right? That's in the real case. In the complex case, this has a little bit of a slightly different form. In spirit, it's similar, but actually it says a little bit more than that. For one thing, it says that the inner product between x and z0 must be real, so the imaginary part is 0, and additionally, the real part is positive. Right? So it's not, it is a little bit more than just half of the complex plane or space, because it sets the imaginary part to 0 of that particular component and has positive on the other one. So it's 2n-1 real set or manifold. In fact, it's a 2n-1 real manifold. It's not a complex manifold, it's a real manifold, because you have one real condition. Okay, so this is the omega z0 set. All right, so what now the statement says? Assume that we know, so there is not an oracle to provide a phase, however, we know that the vector x we want to reconstruct belongs to this set omega z0. So in the real case, we know that it's on that particular side of this hyperplane, right? So that's how we fix the global phase vector. In the real case, we have a choice between one orientation or negative orientation, right? And in this case, by providing this omega z0, we know that for any direction, we know which direction to choose. Right? There is one case which is excluded, which is the omega z0 equal to 0, right? But this is somehow excluded from this statement, saying that we know that additionally the vector x is not perpendicular to 0. Right? So with this caveat or additional constraint, we want to estimate the vector x that belongs here from the magnitude of those inner products, right? Technically, we should have no more ambiguity in terms of the phase, because in the real case, between the two possible orientations, you know which one to choose. And in the complex case, again, because this part is real and positive, again, we can obtain the global phase vector as well. So there's no ambiguity left once we assume that x belongs to this set omega z0. So with that statement in mind, that there is no ambiguity at this time, you can ask yourself, okay, if I have to build an estimator for my vector x, how well is it going to perform? Now, the robustness, or the stochastic robustness measure in this case is the following, that among all unbiased estimators for x, so all functions that take the measurement y and give you an estimate for x, so that the expectation of my estimate is actually equal to x, to the true estimate, to the true vector, right? And again, this makes sense because there is no ambiguity left once I know that x belongs to this omega z0. Right? So across all unbiased estimators, the covariance, or rather the covariance of any unbiased estimator is bounded below by something. Right? Now, that something is related to the Fisher information matrix. Right? And you say what should be the inverse of the Fisher information matrix. Yes, except of one additional caveat. In the real case, this is exactly what it is. This is the inverse of the Fisher information matrix. That was 4 divided by sigma square Rx, so the inverse would be sigma squared by 4 times the inverse. In the complex case, however, you cannot perform this inversion simply because the Fisher information matrix, like the Rx, is actually not invertible. Has a kernel, has a vector in its kernel. And in that case, actually, what you have to do is to take the pseudo-inverse, or the Penrose-Moore inverse. It's a pseudo-inverse that actually plays the role of the lower bound here. It's not the inverse of the Fisher, because that one is not invertible. Even though we removed ambiguity in terms of the global phase, nevertheless, from the estimator perspective, that that Fisher information doesn't capture this constraint. That's, I think, the reason. The Fisher information metric that constructed does not capture the fact that the reconstruction must stay on some half space. And because of that, the Fisher information is not invertible. Has rank 2n minus 1, and it has a pseudo inverse, which is about the lower bound. But that's in some sense the kicker in the complex case. It's slightly different than the real case. But nevertheless, I mean, the forms are similar, which is good. These are the Cramer-Rao lower bounds in this case. Any questions so far, by the way? Okay. So I mentioned the no oracle case because there exists actually a second case, which maybe is much more natural, so-called the oracle case. So for the estimation, the oracle case works like this. We have the same measurement y, right, the magnitude square plus noise. This is our estimator, omega 1, that gives something, a vector. But then the oracle comes into play and says the following. Okay, this is if the estimate that this estimator does, the oracle has access to the true x and figures out what is the best phase factor. Based on that, you put them together, you multiply, and this is the end estimate. Right? In some sense, this is more natural because if you don't really care about the actual global phase factor, perhaps the oracle provides a global phase factor, and I want to know the performance for such an estimator. Okay, so as before, we assume that we deal with unbiased estimator, so the overall, if you do expectation of this output omega, I like to be x. Right? Here you don't have to have any assumption about x as being on some half space or the other, because that ambiguity is taken care of by this oracle. Yeah, that puts back the phase. And what you end up with here should be something comparable to x itself, right? Because the best phase. Well, and as I said, it's the best phase, so it's this is the phase that the oracle returns. It's exactly if you have the correlation between x, the true signal, z, which is the output here of the first part, divided by the magnitude of this character, the phase that the oracle will do. The question is, okay, what about the performance bound in this case? The mean square error, or the covariance for such an estimator if it's unbiased. What can you say about that? And specifically comparing to the no oracle case, the previous, right? Just the fact that it has an oracle that gives you this additional phase vector compared to the case, well, I don't have that one, but I do, however, make the assumption that x stays in half space, right? How the two compare, right? Well, to the truth, I don't know actually. I think it's still an open problem as far as I'm concerned. And get some very interesting but nasty integrals to actually want to try to actually compute the Cramer-Rao lower bound. It goes through the whole derivation, the Fisher information and so on. It actually doesn't. And yeah, so anyhow, it's an interesting problem. That's, I think. Okay, I'd like to spend a few more minutes just briefly discuss one of the Lipschitz bounds. So we are now in the deterministic set. Okay, so we insist on an exact inversion on the range. So we insist on having a left inverse of this map alpha. So we want a map omega, so that omega of alpha of x hat is x hat, so it's a left inverse. And we want to characterize the Lipschitz bounds for this map omega, the Lipschitz constant, which in turn means also Lipschitz bounds, upper and lower Lipschitz bounds for the map alpha. Well, there are several kind of distances or metrics you can introduce and consider on H hat on the space of equivalence classes. One is actually something that I mentioned earlier, but the second one actually is going to be more interesting in the following. And it measures the distance between two vectors as, for instance, the nuclear norm of the difference between rank 1s. You have a vector, x. You associate the rank 1, which is xx star. This is what this notation is, xx star. Vector y, yy star, this is a rank 1 associated. And these are well defined and unique given the classes x hat and y hat That is, if you multiply x by a constant phase vector, the rank 1 stays the same for y. Right? And then you just compute the nuclear norm of the difference. The nuclear norm being the sum of singular eigenvalues. In this case, each of them is rank 1, the difference is going to be rank 2, and then you have 2 eigenvalues, it's symmetric. One is positive, the other is negative, just take the sum of the absolute values of them. The positive plus absolute values negative. Because singular eigenvalues will be absolute value. Eigenvalues, right? This is symmetric. That's a distance. That will be a distance, a metric between classes. What we want to compute, so I'm going to concentrate actually on this one. We want to compute the Lipschitz map of the alpha square function. Takes vector x and returns the magnitude square of the Frank coefficients. And we want to find the infimum difference between, this is Euclidean norm of the difference between coefficients here, by distance d1, and the supremum of this ratio. Right? This would be so-called the Lipschitz constant, upper and lower Lipschitz constant. If the upper one is, the sup one is finite, and the infimum one is strictly positive, the map alpha square in this case would be by Lipschitz. Right? And we want to get a feeling about these numbers. Well, in particular, I want the lower bound because the reciprocal of this lower bound provides the upper Lipschitz constant, the Lipschitz constant of the map omega. There's the inverse. And the upper Lipschitz constant of the inverse is actually related to the lower Lipschitz constant of the direct function, the reciprocal. So that's, we want this number, the infimum, to be as large as possible, so that the Lipschitz constant of the inverse will be as small as possible. That measures the robustness of your inversion. Okay. So I'll just mention this result here. So there is some relationship to the symmetric matrices I mentioned earlier. Let me just concentrate on saying that the Lipschitz constants we are interested in for alpha square turns out to be the following. So for the lower Lipschitz constant, it is precisely the square root of the A norm constant we had in the previous statements. So those A node bounds that we described earlier, right, if and only if necessary conditions sufficient for injectivity, the very same A node actually shows up here as the lower Lipschitz constant for this alpha square map. So that's one of the things I wanted to point out, that it's exactly the same A node constant. The upper bound, the B node, is actually, so A node is, and that also shows up in the Cramer-Rao lower bound, by the way. The upper bound turns out to be actually something that is computable. It's so-called the mixed L2, L4 norm of the analysis operator for the frame. Somehow this is what turns out to be exactly the B node. So think of your analysis operator for your frame set as mapping the Hilbert space with L2 norm there into the space of coefficients, a vector, right? But with L4 norm on the space of coefficients. And that particular norm is actually the upper Lipschitz constant here. For example, that's what it turns out to be. All right, so there is a similar analysis for the other kind of distance. I'd like to skip that one in case like I can provide more information on that one. We know a little bit more about that one in terms of how to compute in the real case, but yeah, I'd rather concentrate on the last topic, which is the algorithm. Do you have any questions so far about the one? So just briefly mention the algorithm. So we came up with so-called iterative regularized least square algorithm. And technically what we'd like to do would be to minimize such a functional. So we have yk as a measurement. This is an n-dimensional vector of real numbers. And we seek a vector x so that the fkxx, this is the magnitude of x fk squared. If you look at the L2 norm of the difference, we want to minimize the x. Right? In the real case, or complex case, actually is like that. But in the complex case, it reduces to, if you want to deal with real vectors with this metric capital K. So, ideally, this is what we want to optimize. This is a least square estimator and the maximum likelihood estimator in case of Gaussian white noise. As the additive as our noisy model. Now, while this is what we want to minimize, the problem with this criterion is that it's not convex. Why it's not convex? Well, you have a quadratic here in x inside, but then you square again, so you end up with a quartic. sum of quartics and you want to minimize. And that's far from being convex, has lots of local minima and so on. How do we deal with this? Well, and this is what the algorithm does. So we're going to introduce actually what I call an homotonic optimization procedure, which two ingredients, regularization and split. And here is a function. So instead of this j, we replace by something else. It's a function that depends now on two vectors, two n-dimensional, and two additional parameters, lambda mu. First, the quadratic here, fkxx or pkxi, we split into pkxi eta. Right? So if psi equal to eta reduces to that one. But if not, well, you have just the quadratic in two vectors, psi and eta. Okay? Additionally, we regularize with psi eta vectors like this. So lambda measure or penalize the psi and eta vectors, and mu penalize the difference between psi and eta. Right? So ideally, so J criterion is related to this one. If we set psi equal to eta and lambda, let's say, to 0, it doesn't matter, then this one reduces to that one. This is what we want to do. Instead, we're gonna, through the splitting, we have two vectors, psi and eta. Now, the advantage of this one, you can rewrite in terms of the vectors, the complex case, u and v and fk and so on. Nevertheless, the advantage is writing psi and eta parts is that in each of them individually is quadratic. Therefore, fixing one is quadratic and the other one is convex. And the other way around. Not convex in joint, but it's convex in each. Right. So far, so good. Okay, yes. All right, now, the idea of the algorithm is the following. So assume that it's an iterative procedure. So we're going to discuss initialization. But let's assume we have a current estimate, psi t, and I want to go to the next one. So what I do, I'm going to fix, let's say, this psi is the psi t I currently have, and I optimize with respect to the other one. And this becomes my next iterative, psi t plus 1. Right? So that's the idea of this marching of this iterative procedure. From psi t, you go to psi t plus 1 by minimizing over eta vector. Right? Now, you have also lambda and mu parameters here, I mean, this penalty terms. And we have to discuss how, if, and how to adjust these parameters, right? And what difference does it make? All right. But essentially, that's the idea. Now, how we initialize this thing first? First thing first. Well, let's say that you look at the j, uu, lambda, mu, that's psi here and lambda, mu. All right, and you look for a very large lambda. The idea is that you start with a large lambda and then you go down to 0, because I know that lambda 0, no penalty eventually reduces to what I want to optimize. It happens that for a very large lambda, this criterion is actually convex. Right. The reason being, so what lambda does, lambda adds a quadratic term here. So when you're looking at uu, so uv, so this disappears, you have 2 lambda u squared, and here is this fourth term, the quartic term. But very large lambda, this quadratic beats the fourth term around 0 and makes it convex. And turns out that it's convex overall. Right? So overall is convex, and in fact, in that case, for very large lambda, is only one unique optimizer, which is 0. So nothing very interesting. That's extremely high temperature if you want to think in terms of an annealing process. So 0. Now you start decreasing lambda, you cool down temperature-wise, and it happens that the first value of lambda for which you get a non-zero trivial optimizer is actually the largest eigenvalue of this matrix R, which is constructed based on data yk and the frame vector, so something which is well defined. So this is the first value, the largest eigenvalue of that matrix for lambda, for which you get a non-zero solution. And that's exactly how we're going to initialize. We're going to take a fraction of this lambda max, and it turns out that the direction you should initialize is related to the eigenvector for that matrix, and some scaling factor that depends on the eigenvalues and so on. Okay, that's how you initialize the procedure. And then, as I said, we have this iteration, and in the result, I'm going to show lambda decreases, by a factor rho. Think of it like 0.99, so decrease 1% at every start. Mu decreases also, but we saturate at some point. It doesn't set to 0. And we solve that quadratic problem, which reduces to solving a linear problem. That's the advantage. And we stop. When do we stop? Well, either when lambda, so decreasing lambda until is below some value, or we can actually control how far at every iteration we are from the measurements. And if we compute like an equivalent signal to noise ratio, if that's when you reach a preset value, I think that actually is inequality, so it's the other way around. So when the noise is below some level, the difference is below a level, that's when it stops. Okay. That's stopping. Okay, so briefly just to show you some simulation results. So N100 is a complex case, 100-dimensional vector, M800, so redundancy 8 times more vectors. And what I did, I generated a random frame set with redundancy 8. Okay. And random X vector, size 100. And for various level of signal to noise ratio, increments of about 2 dB here, from -30 to +40, we have two curves. The straight line corresponds to the Cramer-Rao lower bound I mentioned earlier, because that's computable. It's well, sigma squared divided by 4 times the pseudo inverse of the power matrix, right? The equivalent of the Fisher. And if there's a trace, it gives exactly this lower bound for this mean square error. And the other part, the blue curve, is actually the mean square error for this outlet. And as you see, I mean, asymptotically, with respect to the signal to noise ratio, we approach the Cramer-Rao lower bound. It's asymptotically efficient. Right, efficiency if you reach that CRB. This is for a different redundancy, 6, 4. So you have various levels. And I'm pretty much out of time, but you know, I did some. I mean, there are more results, of course. For redundancy 8, you can have average number of iterations, so you can have a feeling somewhere around 40, 38 to 48. And these are the components bias and variance, this mean square error. You can actually break that where the error comes. And the trace for one such realization, when you iterate, you know, how far you go, how far you are from the solution, it starts oscillating like 0 dB. And things like this. For 40 dB, a very high signal to noise ratio, almost no noise, you know, the error goes down nice and or 0, right? It's in dB scale, so it's negative. And well, here are my conclusions. So we analyze the necessary sufficient conditions for injectivity, for invertibility of the nonlinear map alpha. We obtain the explicit expression for Fisher information matrix and according to the Cramer-Rao lower bound in the real and complex case. And also, those turns out very interestingly, they are related to the Bad-Lipschitz constants, which are deterministic bounds for the inversion. And finally presented, and we analyzed this regularized least square algorithm. I mentioned much about convergence and some robustness to noise, but there are some results about that. We have results about how far it is from the interesting bit. I guess I'm going to stop here, and if you have any questions, I'll be happy to answer.
We thank you first.